Okay, section 4.3 more or less connects to the first two sections. Maybe it connects more to 4.1 than it does 4.2 because there aren't any odds in section 4.3. In fact, I don't think there's odds anywhere else in the rest of the chapter. So section 4.1 kind of could have been placed anywhere in the chapter, but well, it couldn't have been. Section 4.2 couldn't have been section 4.1 because you needed to do some basic probability first. But section 4.2 is probably the section that doesn't fit in with the other sections in the chapter so well. So in section 4.3, we learned something called tree diagrams, which is a tree diagram is a pictorial way to create a sample space for problems where it's just not that easy to visualize the sample space. So far, we had a sample space for rolling 2 dice, which wasn't made with a tree diagram. We had like the sample space of rolling 1 dice. Sample space of rolling 1 dice was the numbers 1, 2, 3, 4, 5, and 6. That's too simple to need a tree diagram. But a little bit later in this section, we'll be given problems like a coin is flipped 3 times and a sequence of head and tails is created. Create a sample space of all the possible outcomes from that experiment. To do that kind of experiment, it's probably not intuitive what the sample space will consist of, and a tree diagram will help us organize the experiment in such a way that we can create all the possible outcomes of a specific experiment. And the other thing we're going to talk about in this section is the counting principle. And the counting principle is a theorem that helps me figure out answers to how many questions. Like, I don't know, if my combination lock has the numbers 1 through 30 on it, and I have to do a left-right-left combination, how many different combinations are possible? Or my ATM code consists of 5 numbers from 0 through 9. How many different ATM codes are possible? Those types of questions, we're going to use the counting principle to figure out how many possibilities there are without even having to list all the possibilities. And so this section starts off with the counting principle. This section, of all the sections, I think probably took me the longest to write, which probably means it's the worst. Usually if things don't come out real naturally and you really fight them, then they're probably not what they could be, but it is what it is, so hopefully it's reasonable. So the counting principle, and it's written, the definition here is written very mathematically precise, and as we get through the section, almost every problem in this section will use the counting principle, and eventually you won't even, well, you might not think of this definition as you do the problems ever, but pretty soon you'll forget the definition and just apply the principle. So the counting principle says if 2 experiments are performed, experiment M first and experiment N second, then there are M times N ways to do experiment M followed by experiment N. That's essentially what this says. If 2 experiments are being performed, M first, N second, and if M has M ways it can, or if the first experiment has M ways it can be done, the second experiment has N ways it can be done, then the first experiment followed by the second experiment has M times N ways that it can be done. That was a really butchered explanation of the counting principle, but I'll leave it be and get into the problems and then try to explain how we're going to apply this theorem in the applications of problems. And so this is the first application. Use the counting principle to find the number of possible experiments of these 2 experiments done in this order. Experiment 1, a coin is tossed and the side that is face up is recorded. So when a coin is tossed, there's 2 possible outcomes. A head could come up or a tail can come up. So experiment 1, there's 2 possible outcomes. Experiment 2, a single 6-sided dice is rolled, and the number that is face up is recorded. So for this experiment, what can happen are the numbers 1, 2, 3, 4, 5, or 6 can come up. So for the first experiment, there's 2 possible outcomes, heads or tail. The second experiment, there's 6 possible outcomes, the numbers 1 through 6. And then the counting principle will tell me how many different outcomes there can be if experiment 1 is performed first and experiment 2 is performed second. For example, something that might happen is the coin might come up a head and the number might come up a 3, or the coin might come up a tail and the number may come up a 1. The counting principle is going to tell me how many different outcomes of flipping a coin, writing down whether it's a head or tail, and rolling a 6-sided dice and recording the number, then recording the results one after another. The counting principle says if I multiply the number of outcomes of the first experiment times the number of outcomes of the second experiment, that will give me the number of outcomes, different outcomes that have the first experiment result first and the second experiment result listed second. In this case, there's going to be, for the first experiment, there were 2 outcomes that were possible. For the second experiment, there were 6 outcomes that were possible. The counting principle says that if I were to list all possible outcomes of a head or a tail on the first experiment and any number from 1 through 6 on the second experiment, there's going to be 12 items that make up that sample space. There's 12 possible outcomes. So the counting principle does a nice job in answering how many questions. How many ways are there to flip a coin and roll a dice? How many different outcomes can there be? But it doesn't list the outcomes. Those are 2 of the outcomes, but there's supposed to be 12. A tree diagram, what it does is it does a wonderful job in listing all the possible outcomes, and it helps you create a sample space. So this is what I want to do next. I want to create a sample space for the experiments that I just referred to. And there should be 12 elements in the sample space because the counting principle tells me how big the sample space is. So my experiment 1 was flipping a coin and recording a head or a tail. And my experiment 2, and these things are weeks to call them experiment, is rolling a dice and recording a 1, 2, 3, 4, 5, or 6. A tree diagram is a way to list the sample space and make so you don't duplicate items in the sample space and make sure you don't miss any. The counting principle told me since there were 2 ways the first experiment can have 2 results for the first experiment, 6 results for the second experiment, there's going to be 12 results in total. What I'm going to do is I'm going to make a branch or a V, or I don't know if you call that a V anymore. How about a less than sign? And above the ends of my V, I'm going to write first experiment. And my first experiment could come up a head, or it could come up with a tail. So what I'm doing is I'm creating something called a tree diagram, and the tree diagram is going to help me list the sample space, which is going to be all 12 possible outcomes. Okay, the reason I have 2 branches, or kind of a less than sign for my first experiment, because my first experiment only has 2 possible outcomes. From the head and from the tail, I need to make room for each of the 6 outcomes that could happen on my second experiment. So from the head, I'm going to make six, we call them branches, and at the ends of the branches I'm going to put the numbers that are possible for the rolling the dice, so I can get a 1, 2, 3, 4, 5, or 6. I'm going to do the same thing from the tail. I'm going to make 1, 2, 3, 4, 5, 6 branches, and I made them go down because I didn't want my branches to overlap, and they don't have to be that pretty. My typed up version is kind of pretty. Alright, now I'm going to try to get a sample space from this diagram by following each path that's described. The first path that I've just circled, that's getting a head by flipping the coin and getting a 1 by rolling my dice. I'm done with this 1. I'm going to cross it out. I'm not going to use it anymore. And now I'm going to figure out the path to get to this 2. The path to get to this 2 is getting a head when you flip the coin and getting a 2 when you roll the dice. I've used up this 2. I'm going to cancel it out, figure out how to get to this 3. To get to this 3, I needed to have a head when I flipped the coin and a 3 when I rolled the dice. I'm done with that. Figure out how to get to this 4. To do that, I needed a head when I flipped the coin, a 4 when I rolled the dice. Cross it out. To get to this 5, it's a head when I flip the coin, a 5 when I roll the dice. Cross out the 5. Figure out how to get to that 6. Get to that 6, that's a head when I flip the coin, a 6 when I roll the dice. So I'm kind of done with the top of my tree diagram. Now I'm going to work my way to the bottom. To get to this one, I have to get a tail when I flip the coin and a 1 when I roll the dice. Did that. Now I'm going to figure out how to get to that 2. To get to that 2, I had to have a tail when I flip the coin and a 2 when I roll the dice. Cross it out, figure out how to get to that 3. That's when I get a tail when I flip the coin, a 3 when I roll the dice. Then to get to this 4, it's a tail when you flip the coin, a 4 when you roll the dice. To get to that 5, a tail when I flip the coin, a 5 when I roll the dice. And to get to that 6, a tail when I flip the coin, and a 6 when I roll the dice. This is the entire sample space using a tree diagram. So this right here is called a tree diagram. And I used tree diagrams to create sample space. This right here is called the sample space for the experiment, flipping a coin and rolling a dice. Now this sample space isn't written maybe as nicely as it could, because generally sample spaces are sets, and we usually write sets in set notation. So it might be nice if I named this maybe S for sample space and put my stuff in a set brackets, and that's what I think I do when I typed it up. So rather than writing this nicely, I'll take advantage of what I have typed up. So this is the sample space. This is the tree diagram that I typed up. It's exactly the same thing that I wrote, but I couldn't figure out how to make these bigger without destroying where my arrows went, and it was getting to be a disaster to try to make this bigger, so I figured I would just write it up by hand. And now here's my sample space. My sample space has the 12 elements in it. I put it in set braces because it's a set. There's a head 1, head 2, head 3, head 4, head 5, head 6, and then because my font was so big, tail 1, 2, 3, 4, 5, and 6 made it on the second line. So the counting principle, it tells me how many items will be in a sample space if you do 2 experiments in a specific order. A tree diagram helps me list the elements of the sample space. They kind of work hand in hand. The counting principle tells me how many items should be in my sample space. The tree diagrams help me create my sample space. Here, there are 12 items, and I knew there should be 12 items. So if the counting principle told me there was going to be 14 items, and I did my tree diagram and only got 12 items, then I probably messed up on my tree diagram. Or I messed up using the counting principle, but they should work hand in hand. The number that the counting principle tells you is going to be the same number of elements in your sample space. Okay, here's another combination counting principle tree diagram problem. So in this particular problem, we have a bag of balls, and in my bag of balls, it has 1 red, 1 blue, 1 green, and 1 orange. And I'm going to select 2 balls, one at a time from this bag of balls. And the questions are going to be posed to me. How many different outcomes are possible? And in order to do this, so and I wrote how many different outcomes were possible. This is the same as the question, use the counting principle to determine the number of points in the sample space. So more generically, for this is actually 2 experiments. An experiment in this case is taking a ball from the bag. So I could have said how many different outcomes, and I won't fit different, so I'll say outcomes are possible. And that has the same meaning to somebody that reads mathematics as use the counting principle to determine the number of possible points in the sample space. So I have to treat this as 2 experiment. So experiment 1 is to remove 1 ball from the bag. And for experiment 1, there's 4 possible outcomes because there's 4 balls in the bag. Experiment 2 is going to remove another ball, a second ball, from the bag. Now, the big key word in this problem, I bolded it, I underlined it, I did what I could to make it important. When it says without replacement, this assumes if you do 2 experiments in a row, that the ball that you take out isn't placed back in. If it said with replacement on experiment 2, the ball that I removed from experiment 1 would be placed back in it and have a chance to be pulled again. So from experiment 1, I could have pulled any one of the 4 balls out. It doesn't matter which one. There are 4 possible ones to pick. Regardless of the one that I pick, the remaining bag is only going to have 3 marbles in it, or 3 balls in it, because I'm not going to place back, because it says without replacement, I'm not going to place the ball that I picked back in. So experiment 2 only has 3 possible outcomes, because there's only going to be 3 balls left in the bag when I take one of the 4 away. The counting principle says the number of possible outcomes, or the number of elements in the sample space, those are interchangeable words, would be 4 times 3, because it's the number of ways the first experiment can be performed, which is 4, times the number of ways the second experiment can be performed, which is 12. So the answer to use the counting principle to determine the number of points in the sample space, the number of points in the sample space is going to be 12, and that's equivalent to the number of possible outcomes is 12. So we kind of use those interchangeably. And that's exactly what I showed here. And again, once I started using these arrows, things just didn't blow up that well. So the answer is 12. The next thing I want to do is actually construct a tree diagram. And to construct my tree diagram, I'm going to need to make a first and a second level of my tree diagram. And again, for the balls here were red, blue, green, and orange. I'm going to call red R. I'm going to call blue B. Imagine that. Green G, and then orange I'm going to call W. No, I'll call it O. So I'm going to make a tree diagram to illustrate what can happen. So picking a ball, not putting it back, and then picking another ball. So I'm going to make my first level of my tree diagram for the first ball that's selected, and it's going to start out at a point, and from the point it's going to have 4 bars or 4 lines coming out of it, because the first ball can be blue, it could be red, blue, green, or orange. Once I pick a ball, I'm not putting it back, and so there's only going to be 3 balls for the second ball. So from the red, I'm going to make 3 lines. From the blue, I'm going to make 3 lines. From the green, I'm going to make 3. And for the orange, I'm going to make 3. This is because after I pick a color that's gone and I can't pick it again. So from the red, if I pick the red, it's no longer going to be in the bag. What's left is blue, green, and orange. So if the red is picked first, it can't be picked again, and the only ones that can be picked for the second one are the blue, the green, and the orange. And then in terms of my sample space, this would be getting a red first and a blue second. This would be getting a red first and a green second. This would be getting a red first and an orange second. If the first marble picked is, or first ball picked is blue, then you can't get a blue again because it's without replacement. It's not going to be placed back. The second ball can only be red, green, or orange. And it wouldn't matter which order you write these in. You could have said green, orange, and red. It would have been fine. In terms of the sample space here, this would be getting a blue first and a red second, a blue first and a green second, and a blue first and an orange second. Not done yet. I only have 6 of the 12 items in the sample space. If the green is selected first, then I could get a red, a blue, or an orange for the third, but I couldn't get a green because I'm not putting it back because of the without replacement. So this is going to have a red, a blue, and an orange. And so now I'm going to write green, red, green, blue, green, orange. There's 9 items of the 12 in the sample space. Part A of this problem told me there should be 12 points in the sample space, or 12 elements in the sample space. And I'm using my tree diagram to get them. If the first is orange, I can't get an orange for the second one. I can get a red, blue, or green for the third. And in terms of the sample space, this is going to be orange and red. This is going to be orange and blue. This is going to be orange and green. Not every sample space is going to have 12 items in it. In fact, it's probably going to be rare for a sample space to have 12 items in it. So this is the sample space, or these are the elements that make up the sample space, and there's 12 of them. So the counting principle told me that there would be 12 items that make up the sample space, but it doesn't tell you what the items are. Tree diagrams help you list the sample space. Of course, if you could list the sample space without using a tree diagram, tree diagrams aren't necessary. They're just a tool to assist you in creating a sample space. And quite honestly, because I've done this enough, I can do sample spaces for the most part without tree diagrams. So if you're clever enough, you can, and I ask you to use a tree diagram to make a sample space, and you can get the sample space correctly without using a tree diagram. You don't really have to. So again, it's probably nice if I write the sample space in set notation. There's my 12 red, blue, red, green, red, orange, blue, and all 12 items that were listed in my sample space. I wrote them in set brackets. I probably should have just called that S for sample space rather than writing the word sample space, but that's fine. Now a probability question. So now this is connecting to section 1. So part C, so I'm going to use my sample space to answer a probability question. The question is, what is the probability that Anne on orange ball is selected? Well, probabilities in general, we form fractions. The numerator is the number of occurrences that have the desired characteristic. The desired characteristic is at least one of the balls is orange. The denominator is the total number of outcomes, or the total number of items in the sample space. So to do this probability, I need to look at my sample space. There's 12 items in my sample space, so the denominator of my probability is going to be 12, because when we do probabilities, the denominator is the number of items, things that can happen. In this case, it's the size of the sample space, which is 12. Within the sample space, there are a bunch of O's, and any one of these items in the sample space that has an O is going to be considered okay for the numerator, because the numerator, its requirement the probability, we're trying to find out the probability that an O was selected or an orange was selected, and there's 6 items that I just boxed, so the numerator of my probability should be 6. So the probability that one orange ball is selected is, in the numerator, the number of items in the sample space with one orange ball, which is 6. The denominator, the number of outcomes, or the size of the sample space, which is 12. So it's 6 and 12, which reduces to 1 and 2. Okay, same sort of question, but I changed one word. I changed the word without to with. So it's exactly the same. So we have this bag of balls, and it has one red, one blue, one green, and one orange. And I'm going to do 2 experiments. Experiment 1, experiment 1 is to remove one of the balls. And in this case, there's 4 things that can happen on experiment 1. I can pull out the red, the blue, the green, or the orange. Experiment 2 is I'm going to remove one ball after I put back the ball selected in experiment 1. So the with replacement part tells me that it doesn't matter what you pick the first time, you could still pick it again. So experiment 2, I'm going to be drawing from a bag that has the same 4 balls in it, and there's going to be 4 ways to experiment 2 can be performed. The counting principle says there are 4 times 4 ways to do experiment 1 followed by experiment 2. So there's 16 different outcomes that are possible for this experiment as opposed to the 12 that were possible in the last experiment. So without replacement, you always get a smaller sample space. And again, I had to think of this problem as having 2 experiments. I'm taking 2 balls out, one at a time, taking the ball out, looking at it, noting its color, putting it back in, shuffling them back up, picking out another one. Each experiment is removing a ball. So there's 16 different items. The size of the sample space is going to be 16. The counting principle says there's 16 different possibilities when I do an experiment, 2 experiments this way. Remove a ball, put it back, remove another ball. Let me make the sample space, even though I didn't ask to make the sample space, just so you should be able to do this. It's kind of a nuisance to do the sample space because it has 16, but we need to be good at making sample spaces. So again, we have experiment 1, which is going to be getting the first ball, and my first ball can be red, blue, orange, or green. And then for ball 2, it can be any one of the 4 still. So from the red, I'm going to make 4 arrows, and I'm going to put red, blue, orange, green. And the top here would be getting a red first and a red second, which you can do because you're putting the red back. And then red, blue, red, orange, red, green. And it doesn't matter the order that you write the elements of the sample space, and I think I flipped up the orange and the green, but it doesn't matter. I'm going to do the same thing from the blue. I'm going to make the 4 dashes from it, or the 4 lines from it, and put the same letters, red, blue, orange, green. And this would be getting a blue first and a red second, a blue first and a blue second, a blue first and an orange second, and a blue first and a green second. And then from the orange, do the same. So red, blue, orange, green. So orange first, red second, orange first, blue second, orange first, orange second, orange first, green second. And then the same from the green. Again, the difference between this problem and the last problem is you can get the same color twice because it's with replacement. I'm placing the ball back in. So this is the sample space, and if you count, there's 16 items in the sample space, and that's what the counting principle told me. The counting principle said doing these experiments picking a ball out from these 4 balls, putting it back, and then picking another ball out, there was going to be 16 different outcomes. So the counting principle tells me how many outcomes there are, but doesn't tell me what the specific outcomes look like. Tree diagrams help me create the specific outcomes. Sometimes it's enough just to know how many, and other times you need to see the whole sample space. And the homework in this section, the first part of the homework asks just a bunch of problems to use the counting principle without listing the sample space, and then we get into a bunch of problems with use the counting principle to figure out how big the sample space is, create the sample space, and then answer a probability question. Okay, so this next problem, it doesn't look anything like what we've done before, and it may not feel like a counting principle problem, but I can handle it like a counting principle problem. So Joe has 7 shirts, 4 pairs of pants, and 2 pairs of shoes. He needs to make an outfit containing one of each item. This is kind of a classic beginning counting principle problem. If you took discrete math in high school, you may have seen something exactly like this. So how many different outfits are possible? And then, so like just changing a pair of pants, like if I had my, my green shirt on and my jeans and my black shoes on, if I had the same shirt and the same pants and I changed it to my brown shoes, we'd consider that a different outfit, even though you might not consider it. But in terms of the counting principle, changing one of the items of clothing is going to create a new outfit, even though, it look essentially the same. So it won't be that different, some of the outfits. So this is a counting experiment problem. It has 3 experiments as opposed to 2, and the counting principle can be extended to 100 experiments if you want. You'll just, if you know the number of outcomes for each experiment, you just multiply those numbers, and that will give me the number of possible outcomes. So experiment 1 is selecting a shirt, experiment 2 is selecting a pair of pants, experiment 3 is picking a pair of shoes. Selecting a shirt, there are 7 possible outcomes because there's 7 shirts. Picking a pair of pants, there's 4 possible outcomes because there's 4 pair of pants you can choose from. And selecting a pair of shoes, the 3rd experiment, there's 2 possible outcomes because he has 2 pairs of shoes. The counting principle says doing experiment 1 followed by experiment 2 followed by experiment 3. If you know the number of outcomes of each experiment, if you just multiply those outcomes together, you'll get the number of possible items in the sample space, and the items in this sample space are the different outfits that Joe would have, consisting of 1 shirt, 1 pair of pants, and 1 pair of shoes. So that's 56 different outcomes. We're going to do a boatload of problems coming up just like this. And problem 1 in the homework is this, but I don't think problem 1 you'd be ready to do right yet. So I'm going to do problem 2, then I'll let you look at problem 1, because problem 1 and 2 both use the counting principle, but in a little bit different way, and I just didn't want to do a million examples. I thought I'd just jump into the problems, and then we'd figure it out as we go. So I'm going to assume in problem 2 that, like, I have each of the days of the month of May listed and maybe on slips of paper and put in a hat. So maybe I have in a hat something that says like May 1, May 2, all the way up to May 31st. So I have each of the dates in May listed. They don't really need to be on a sheet of paper thrown in a hat, but maybe it's nice to visualize it that way. So I have these 31 slips of paper, each one with the month of May and a day in May, and there's 31 days in May. And what I'm going to do is I'm going to select 2 dates at random. So I'm going to select 1 date, and in part A, I'm going to put the date back, and then I'm going to select a 2nd date. The counting principle is going to tell me how many possible outcomes. The first experiment is picking the 1st date. The 2nd experiment is picking the 2nd date. So I'm going to use the counting principle, and I'm going to start to get a little bit slicker. So the counting principle makes me create experiments, and my experiment is picking a 1st date for the 1st experiment, picking a second date for the second experiment. The first date, if I go through my hat and I pick out one of these slips, there's 31 different slips that will make up the possibilities for the first date. The fact that this says with replacement, whatever date I pick for the first date, I'm going to put it back in my hat. That slip of paper is going to go back in there. And when I go to pick the second date, all 31 days in May will still be available to me to select from. So the counting principle says there's going to be 31 times 31, which is 961 different items in the sample space. Like it might be, I might have picked, May 4th, then May 11th. So the items in the sample space are going to look like that. Well, I'm not going to list all the items because there's 961 of them. That's just one of 961. Another one would be like May the 21st and May the 16th. So the items in the sample space that this is counting looks like that. And never would I make you create a sample space that has 961 items in it. That would just be insane. So in these questions, the first 19 problems, we're going to answer how big the sample space would be without actually creating the sample space. Part B of question 2 is the same experiment. I'm taking 2 dates out from the month of May, but I'm not putting the first one back. So it's a similar setup. My first experiment is picking the first date. My second experiment is picking the second date. For the first experiment, I can pick any one of the 31 days in May. And then when I pick a day, I'm not allowed to pick it again. So if I picked May 4th for my first day, I can't pick it again. So I need to increment down one. For the second day, there's only going to be 30 days left to pick because one of them's picked, I'm not allowed to pick it again. Whereas in the top place, with replacement, I'm allowed to pick the same day twice. So now I'm just going to multiply 31 times 30. And I get 930. There's always less when you have without replacement than when you have with replacement. So now, with that as an inspiration, it's kind of the same problem. The numbers are going to be a lot bigger. So if 2 dates are selected at random from the 365 days of the year, and then they're listed in the order that they're selected, so maybe I pick April 4th and then November 16th, which hopefully is somebody's birthday, or December 2nd, then November 8th. Those are the things I can do. So my experiment is picking a first date of the year and a second date of the year. So the first experiment is picking the first date, the second experiment is picking the second date, and then you have to decide for the first date how many there are to pick from, and the second date how many there are to pick from, and then you'll multiply those numbers. Well, because there's 365 days in the year, there's 365 days to choose for the first day. The second date is either going to increment down by 1 to 364, or it's going to stay at 365, and that's going to be hinged on these words. When it says with replacement, that means you can pick the same date again. I won't increment down. If I say without replacement, then I need to increment down. So for your problem 1, I'm not done with them because I haven't broken out my calculator, but for both scenarios, there's 365 days to choose from the first day. But in the top scenario, because I'm putting that day, I'm letting that day be picked again, there's 365 days to choose from for the second day. In the bottom scenario, I'm not allowing that day to be picked again. Once it's picked, it's not available to pick again, so there's only 364 for the second date. And you just multiply those out to get your answers. 3 is your problem. It's exactly the Joe problem with different numbers. And my problem is Shannon picking a new car, and the car has 4 exteriors, 2 interiors, and 2 engines. How many different options are possible? Well, experiment 1 is going to be picking an exterior color. Experiment 2 is going to be picking an interior color. It feels bad calling these things experiments, but that's how we have to consider them. And experiment 3 is picking an engine. So there's 3 distinct experiments: an exterior color, an interior color, and then an engine. For Shannon, there's 5 exterior colors, 2 interior colors, and 2 engine options. So I wrote the number of outcomes, possible outcomes for each experiment. And the counting principle says if I just multiply these 3 numbers, that's going to be the answer to the question. So there's 20 different cars. So having a red car with a gray interior and a 4-cylinder engine is different than having a white car with a gray interior and a 4-cylinder engine. If one option is different, then the car is considered different. So your Joe problem should work just the same way. It should work just the same way as the example that we did. So I'm going to do 6, and you might make a stab at 5. If you need to watch me do 6, they're kind of similar. So my safe lock has 3 numbers. So I need to pick a first number. That's my first experiment. A second number, which is my second experiment. And a third number. And I need to find out how many choices are possible for each experiment and then multiply. So my safe has the numbers 0 to 36. That's actually 37 numbers. The numbers 1 through 36 would give me 36 numbers, and then I add the 0 and I get 37 numbers. So for the first number in my combination, there's any one of 37 numbers that are possible. In my instructions, it says no number may be used more than once. So that means the second number can't be the same as the first number. There's one less number to choose because one of the numbers has already been chosen. For my last number, I can't repeat a number. 2 numbers have already been used. I only have 35 numbers left to choose from. So the number of possible combinations, if you can't have double numbers for this safe, is going to be 37 times 36 times 35. Which is 46,620. So these counting principle problems can get really big numbers really quickly. So for your problem, a television remote has digits 0 through 9. You're going to press 2 of these digits. How many numbers are possible? So for you, your experiment is picking a first number and then a second number. Now, for the first number, there's going to be 10 numbers to choose from. The numbers 1 through 9 are 9 numbers, and then 0 gives me a 10 number. So for both parts A and B, your beginning is going to have 10 choices for the first number, because there's 10 numbers, the digits 1 through 9, and then 0 makes 10. The second choice is going to be dependent on the problem. In part A, it says you're allowed to pick the same button twice, so there's still going to be 10 choices for the second number in part A. But in part B, it says once you pick a button, you can't pick it again, so there's only going to be 9 choices for the second. And then you just multiply these. So for part 5A, I'll get 100. For 5B, I'll get 90. Turns out there's a section, I forget, I think it's 4.8, that will relive these problems again. So these problems will come up frequently in this chapter, at least one more time, and probably even more than one more time. All right, so you have for problem 7, you have a movie theater, 3 sizes of popcorn, 3 different toppings. How many different ways can you get a bag of popcorn at this theater? For mine, I have girls' ice skates. They come in 5 colors. They come in 4 sizes, and they have 3 different extras you can have, and all skates are sold with one color, one size, and exactly one extra. We're not going to have any that don't have one of the extras. So what I need, my 3 experiments for here is, first I need to pick a color. That's the first experiment. Then I have to select a size, which is my second experiment. Then I have to pick an extra, which is my third experiment. There's 5 choices for the color, 4 choices for the size, 3 choices for the extras. It would be a way harder problem if you could pick between 0 and 3 extras. That would be monumentally harder. So when I wrote these problems, I had to be really careful to keep them at a level that was appropriate for an introduction to counting. I took a graduate level class in discrete math, and I'm telling you, the problems could look just like this, and they were so mind-boggling hard to count everything that you needed to count. It was really, really humbling. So I tried to make the problems as simple as I can, with still teaching the stuff that I needed to teach, but these problems can get way out of control really fast. My answer for problem 8 should have been 60. Your answer for problem 7, I imagine, is 9. So I'm going to do my problem. Oh gosh. I should probably, unless I have a license plate problem for me, let me get you started with number 9, and then I'll come back and do number 10. So a state issues, this is a classic counting problem too. So there's a state that has a license plate that has letters and numbers. There are 26 letters, and letters may be repeated. There are 10 digits, and digits may be repeated, digits 0 through 9. How many possible license plates can be issued with 2 letters followed by 3 numbers? So what I need to do is 5 experiments. I need to pick the first letter, so letter 1. I need to pick the second letter, letter 2. I need to pick the first number, we'll say number 1. I need to pick the second number, we'll call that number 2. And I need to pick the third number, which is number 3. So there's 5 different experiments, because there's 5 different numbers or letters I need to place on my license plates for problem 9, because there are 2 letters followed by 3 numbers. So I made a spot for each of the 5 choices I had: letter 1, letter 2, number 1, number 2, number 3. For the first letter, because there's 26 letters in the alphabet, there's 26 letters that could be chosen for the first letter. I have to decide if I'm going to increment down or I'm going to keep the number. And because letters can be repeated, I don't have to increment down. If I pick an A for the first, I can pick an A for the second. The interesting thing is, when a state goes to make license, well, let me finish this up and I'll say something that fits. For the numbers, numbers can also be repeated, and I have any choice between the numbers 1 through 9 and 0. So there's 10 numbers for the first number, and it says because numbers can be repeated, so if I picked a 7 for the first number, a 7 can be my second number, it can be my third number. So I'm not going to increment down. You only increment down if you're not allowed to repeat numbers or you're not allowed to repeat letters. If you multiply those, you'll get the answer to this question. Like the Arizona license plates, are they 3 letters followed by 3 numbers now, or maybe 3 letters followed by 4 numbers? I kind of forget what they are. But anyways, when Arizona issues license plates, it's really careful, and it doesn't let 3-letter combinations go out that spell words that people wouldn't want to see, like FUC, I guess would be something. You won't see a license plate that has that. I'm almost certain of that. And there are definitely other 3-letter combinations that I almost think ASS would be one of them. I don't remember if I've ever seen a license plate with that or not, but they're selective in what they will or won't put in a license plate. So even if you want a personalized plate, they will definitely they'll censor you to see. Not that that's important, but that's reality. So to do this problem in reality, if I had to start throwing out certain letter combinations, that's a way more graduated advanced problem. You can finish problem 9, I'll do problem 10. Ice cream shop has 31 flavors of ice cream. You want a double scoop. How many different ways can you put the ice cream on the cone if you want 2 different flavors? So I'm going to get, I need to select a first flavor, and I'm going to assume that only the flavors matter. Like if I had chocolate on top and vanilla on the bottom, that's the same as having vanilla on top and chocolate on the bottom. I might have just said the same thing, but this is first scoop, second scoop, I guess, is the way we're going to do this. And for my first scoop, there's 31 choices because this ice cream place has 31 flavors. I have to read through the problem to determine if I have to increment down or not. And because I want 2 different flavors, I'm going to get a different flavor for my second flavor, and there's only going to be 30 flavors available for my second flavor. So whatever 31 times 30 is, it's 930. So there's 930 different combinations of 2 flavors I could get for 2 different flavors. Again, there'd be no way I'd ever want to list those, you know, like pecan praline and strawberry, which would be a ridiculous combination, but it would be counted here because it would be 2 flavors that are different if those are ice cream flavors that were offered. Alright, so I'll let you take a stab at 11 and I'll do 12. So Elizabeth is choosing silverware which to eat dinner. She needs to pick a knife and a fork, and experiment 1 is picking a knife. Experiment 2 is picking a fork. There are 3 knives to pick from, 2 forks to pick from. So there's 6 different silverware sets that Elizabeth can choose. Now I get my car license plate one. Your problem is easier than mine. I'll take a stab at 14. My car license plate has, I need to pick a first letter, a second letter, a third letter, and then it has 3 numbers. So I need to pick a first number, a second number, and a third number. It says there's no restrictions, which means duplication is allowed. For each of the letters, there's 26 letters that are possible because there's 26 letters in our alphabet. And for each of the numbers or the digits, there's the numbers 1 through 9 and 0, so there's 10 digits to choose from. If I multiply those, 26 times 26 times 26 times 10 times 10 times 10, it'll give me the number of license plates. So 26 times 26 times 26 times 10 times 10 times 10, and I get 17,576,000 license plates, which is a lot, but like in a state like California, where there's, 7 million people in Los Angeles, and a lot of people have multiple cars, you'd run out of license plates. This is why some states, like if you go to, Vermont, which doesn't have many people, they have simple license plates. They might have 2 letters followed by 3 numbers, but California, I don't know what they even are, but I'm sure they will have more than 3 letters followed by 3 numbers because you only get 17 million license plates, and if you start talking businesses, you start to lose up all the possibilities too quickly. Answer question 14, which is for you, but assume there's 2 letters followed by 4 numbers. So how many license plates are possible going letter, letter, number, 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 number? And there's no restrictions, which means you don't need to increment down. New York has 3 letters followed by 4 digits. How many are possible? And I'll get into this. So for New York, we have letter 1. So I'm doing 16. Letter 2, letter 3, and then number 1, number 2, number 3, and number 4. And then how many different license plates are possible? Digits can't be repeated, which means the numbers can't be repeated. So my numbers need to start with 10, and then I can't use a number that I've used, so I need to increment down 1 each time. because I've used one number, I can't use it again. After I've used two numbers, they're not permittable again in this particular problem. That's not reality. In reality, you can have double numbers, but I just wanted to make a problem that was different. And then letters can be repeated, so each letter choice has 26 choices. Oh, there's actually 3 letters. So I'm going to multiply those and get some really large number. So 26 times 26 times 26 times 10 times 9 times 8 times 7, and I get 88,583,040, and that's with restrictions. I mean, New York's not going to have the restrictions that you can't have double numbers. I know that, so it's going to give you more, but then we'll throw some out because there's some letter combinations that they won't let you have. I always thought they shouldn't have license plates that have 666 on it, but yet they do. When I got divorced, my ex-wife got a license plate that had 666 on it. I didn't wish her any ill, but I probably smiled when I saw that the first time. Oh, I'm wearing out, and we've got a long ways to go, so let's just push on here. So 17 and 18, you have a New York license plate one, so, and there's no repetition, so you're going down each time. I have students at a small college are given an ID. The IDs are made up of 5 digits. The digits can be repeated. So we're gonna get your first number and your ID all the way to your 5th number, and they need to go in order. If you scramble the order, you get a different number. So, at this small college, and I think at GCC, we have 5-digit numbers, but they all start with a 3. So that kind of makes this a little bit different. So this would say you could have like 111111 for your ID, or 98765 for your ID. So students in a small college are assigned IDs, and duplication is allowed. So for each choice, there's going to be 10 possible digits that could happen. So for the first number, you can get any number between 0 and 9. And for each of the numbers, you can get any one between 0 and 9. I think I can multiply this. I think there's 100,000 different numbers that are ID numbers that are possible for this school. 19 is the last one of these kinds of problems, and then we'll get into the other kinds of problems where we use the counting principle, create sample spaces, and answer probability questions. So I give you a second to do that. And now we'll move on to the next kind of problem. This is a real classic problem of problem 20. So a couple plans, they have 3 children. Determine the number of elements in the sample space. Well, we have to start understanding these things a little bit differently than we might. So in this problem, a sample space is going to look like something like this. It could be the first child is a boy, the second child is a girl, the third child is a girl. This is what the sample space is going to start to look like. So if a couple's having 3 children, they're going to have an oldest child, a middle child, and a youngest child. And the oldest child could be a boy or a girl, the middle child could be a boy or a girl, and the youngest child can be a boy or a girl. And theoretically, if the first child's a boy, the second child could still be a boy or a girl. Although you see a lot of families with all boys and all girls, it's still possible. There's still 2 choices for each time. So there's going to be 8 items in the sample space for a couple having 3 children. Now I'm going to create that sample space. That's what part B wants me to do. And then I'm going to answer probability questions. Each of the probability questions, the denominator is going to be 8, because there's going to be 8 items in the sample space. Without even knowing anything about the sample space other than it has 8 items in it, I know that if you ask me the probability this couple has whatever, the denominator is going to be 8 because that's the size of the sample space. So now I need to make a tree diagram. And so I'm going to start off with my first child. And the first child can be a girl or it can be a boy. And then I'm going to make room for a second child, which can be a girl or a boy. And then a third child, which can be a girl or a boy. And now I need to get to each item in the far right hand column. To get to this G right here, the path I'm going to have to follow is girl first, girl second, girl third. So this G, the sample space element it's going to have is girl first, girl second, girl third. Done with this, move down to this B. To get to this B, I had to have girl first, girl second, boy third. So the second item in my sample space is going to relate to that B. It's girl second, girl first, girl second, boy third. To get to this G, it's girl first, boy second, girl third. So this G right here represents a girl first, a boy second, and a girl third. Done with it. This B right here represents girl first, boy second, girl third. Done with it. This G represents boy first, girl second. This B right here represents boy first, girl second, boy third. This G right here represents boy first, boy second, girl third. And this B right here is boy first, boy second, boy third. If you count, there's going to be 1, 2, 3, 4, 5, 6, 7, 8 items that make up the sample space. I'm going to go ahead and write the sample space right on this sheet right here. So my sample space that I just created is girl, 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 and then girl, girl, boy, and then girl, boy, girl, girl, boy, 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 girl, girl, boy, girl, boy, 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 girl, and boy, boy, boy. So those are the 8 items that made up that sample space. I just took them from that list. So that's the sample space. Now I can answer probability questions. What's the probability that the couple had 2 girls? Well, I need to count any item in the sample space that has 2 girls. That's 3 girls. That doesn't count. Girl, girl, boy, I count it because it has 2 girls. Girl, boy, girl, I count it because it has 2 girls. I don't count girl, boy, boy, that has 1 girl. I count boy, girl, girl, it has 2 girls. I don't count boy, girl, boy, it has 1 girl. I don't count boy, boy, girl, it has 1 girl. I don't count boy, 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 it has no girls. So in the sample space, there are 3 items that have 2 girls. So the probability that the couple has 2 girls is 3 in 8. Because there's 8 items in the sample space, so the denominator is 8. There's 3 items that have 2 girls, so it's going to be a 3 in the numerator. For at least 1 girl, that would be 1, 2, or 3 girls. So the GGG, that's at least 1 girl because it has 3 girls, so I'm going to count it. So each item in the sample space, I'm going to figure out if I'm going to count it or not. So I'm going to count that because it has at least 1 girl. And then GGB, I'm going to count it because it has 2 girls, that's at least 1 girl. GBG, I'm going to count because it has 2 girls, that's at least 1 girl. GBB, I'm going to count because it has 1 girl, that's at least 1. BGG, I'm going to count because it has 2. BGB, I'm going to count. And BBG, I'm going to count. But I'm not going to count the BBB. So these are the items in my sample space that fit. They have at least 1 girl, which means 1, 2, or 3 girls. And if I count them, there's 7 of them. So the answer here is going to be 7 over 8. And then this question, how about a girl then? I'll have to change it because it doesn't make sense. A girl then 2 boys. When we do question 21, I think they use the question just didn't make sense because that's only 2 kids and we need 3. So I changed this to be a girl then 2 boys. That's a girl then 1 boy. There's a girl then 2 boys. This right here is a girl then 2 boys, and I don't think there's another one in the list that has a girl then 2 boys. So it's going to be 1 out of 8, modified to make it so I could do it. So this is your problem. Your problem's a heck of a lot easier, and this question makes sense in your problem. You're having a couple with 2 children. You're going to figure out the size of the sample space and then make a sample space with a tree diagram. So for you, you're going to have a first child and a second. There's 2 children that you could have a boy or a girl first and a boy or a girl second. Your sample space is just going to have 4 elements in it. And to get your sample space, you're going to have first kid and second. So this could be like having a girl first and a girl second. This is having a girl first and a boy second, a boy first and a girl second, a boy first and a boy second. So those are all 4 elements. There's your sample space. Each of the probability questions is going to have a 4 in the denominator because the sample space has 4 items. So most of this problem is done. You need to knock out the probability questions. Like for part A, the probability a couple has 2 girls, the denominator is 4 because there's 4 elements in the sample space. The numerator is going to be 1 because there's 1 element in the sample space that has 2 girls. And you just answer them the rest of the questions. So you're going to have to pause the video to finish that. This is a horrible question. When I saw problem 22 just a minute ago or an hour ago before I started this lecture, I'm like, why would I do that to myself? This sample space is going to have 16 items in it, and it's too big. So there's a couple having 4 children. So we're going to have a first, a second, a third, and then a fourth. And there's 2. Each one can be a boy or a girl. So there's 2 possibilities for each kid. The sample space is going to have 16. This question, I'm just going to cross that out and pretend it doesn't exist, and I'll do the other ones. So now I'm going to make my tree diagram. It's going to be big because it needs to have 16 things on it. So I'm going to start off giving myself a lot of room. So for a first kid, it could be a girl or a boy. And then for a second, it can be a girl or a boy. And then a third still can be a girl or a boy. Forgot the second down here. Third. Unfortunately, I need to go 1 deeper and get my fourth. And let me just start cleaning these up. So this G right here is G, 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 G. So it's all 4 girls. So girl, 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 girl. This B is girl, 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 boy. And then I'm going to put a GB here. This G right here is girl, girl, boy, girl. This B right here is girl, girl, boy, boy. And then GB here. This G is girl, boy, girl, girl. This B is girl, boy, girl, boy. This, done with that. This G is girl, boy, boy, girl. This B is girl, boy, boy, boy. That's 8. I need to get 8 more. So now, come down here. This G is boy, girl, girl, girl. This B is boy, girl, girl, boy. This G is boy, girl, boy, girl. This B is boy, girl, boy, boy. And then same down here. This G is boy, boy, girl, girl. This B is boy, boy, girl, boy. This G is boy, 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 girl. And this B is all boys. Ugh. There's 16 items there in the sample space. That's a nasty sample space. I'd never have you do that on a test. Let me just write it on this sheet. So, girl, 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 God, girl, 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 boy, girl, girl, boy, girl, 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 boy, boy. Really? Oh my gosh. Girl, boy, girl, girl. F. I'm not going to write it there. I don't have. I'm going to leave myself enough room. So let me clean this up. Sample space. Girl, 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 girl. I write too big. Girl, 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 boy. This is insane. Girl, 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 boy. And then girl, girl, boy, girl. And then girl, girl, boy, boy. Ugh. I'm just copying from that sheet. And then girl, boy, girl, girl. Girl, boy, girl, boy. Girl, boy, boy, girl. And girl, boy, boy, boy. I'll just write the rest down. So there's 16 distinct items in this sample space. And to answer probability questions, I need to be able to filter through the sample space and find the ones that have the characteristic that's required. So this is the sample space. And again, I won't ever make you make such a horrible sample space. So there's my tree diagram. I lifted the sample space. Now I'm going to answer the probability questions, and just 2 of them. Each of the denominators is going to be 16 because there's 16 items in my sample space. For part C, they have exactly 2 girls. That's 4 girls, 3 girls, 3 girls, 2 girls. I'm going to count it in part C. And then 3 girls, 2 girls, I'm going to count it. 2 girls, I'm going to count it. 1 girl, no good. 3 girls, no good. 2 girls, good. 2 girls, good. 1 girl, 2 girl, 1 girl, 1 girl, no girl. So in part C, what I'm counting is 1, 2, 3, 4, 5, 6 of these choices have exactly 2 girls. So the numerator is going to be 6 and 16, and I'm going to reduce that to 3 and 8. Of course, I'll make sure I didn't miss anything. I don't think I did. For part D, it's at least 1 girl. So anything that I highlighted so far had at least 1 girl. In fact, almost everything has at least 1 girl. That would be 1, 2, 3, or 4 girls. For part D, all of those fit that they have at least 1 girl, and there's 15 of those. There's only 1 of them that is doesn't have any girls. So the probability they have at least one girl is 15 in 16 if they have 4 kids. Horrible problem, but it is what it is. So hopefully we don't have to experience that again. Turns out that in the world of probability, having children and tossing coins they're structurally the same. So in this problem, a coin is tossed 3 times and a sequence of heads and tails is recorded. We're going to do the sample space just like the boy and girl sample space, except instead of B's and G's, you're going to have H's and T's. So you might be able to do that by yourself, or you can watch me do mine. And I picked the easy one for me this time because I just did the horrible one. So I'm going to flip a coin 2 times and answer some probability questions. So for me, how many items are in the sample space? We have a first flip and a second flip. The first flip can come up heads or tails. The second flip can come up heads or tails. There's going to be 4 items in my sample space. I can do my sample space here because it's so small. So we have a first flip, which can be head or tail, and a second, which could be head or tail. This is so much nicer. This head right here represents getting a head first and a head second. This tail right here represents getting a head first and a tail second. This is a tail first and a head second, and then a tail first and a tail second. So my sample space for this problem has head head, head tail, tail head, and tail tail. For each of the probability questions, my denominator is going to be 4 because there's 4 items in the sample space. So each one of these, my denominator is 4, and then the numerator is the number of things in the sample space that fit the criteria. Part C says no heads is tossed, and for part C, I'm only counting the double tail. That's the only one with no heads, so the numerator is going to be 1. For part D, for exactly 1 head, I'm going to count the head tail, and I'm going to count the tail head, because those 2 have exactly 1 head. So it's going to be 2 and 4, which is I'm going to reduce to 1 and 2. And part E almost doesn't make sense. There's nothing in the sample space that has 3 heads, because at most you have 2 heads. So this is an impossible event. The probability is 0. Much nicer than your problem 23. You're going to have 8 items in your sample space, and you're going to HHH, TTT, HTH, HTT. You'll just list all the items, and you'll answer your probability questions. And your denominators are going to be 8 because your sample space is going to have 8 elements in it. So the tree diagram for 6-sided dice, I usually don't make tree diagrams. So I'm going to do a sample space for 6-sided dice, because tree diagrams, although they'll get me the right sample space, it's not very usable. So what we did in the last section with 6-sided dice, I'm going to make a table to generate the sample space for rolling dice. And I'm going to put the numbers 1 through 6 along the top of the table. And along the side. So this is another way to create a sample space, and it's not a tree diagram, and the only time I use a table to create a sample space is for rolling 2 6-sided dice. So my sample space would be having this dice be a 1 and that dice be a 1, and we've seen this sample space at least, now we're creating it. The sum of these 2 dice is 2. Now having this dice a 1 and that dice a 2, I'm going to write that as a 1 and a 2, and the sum of those is 3, and then a 1 and a 3, the sum is 4. I'm just going to write the number instead of the word sum, otherwise I'll run out of room because I made some skinny boxes. And then 1 and 4 has a sum of 5, a 1 and a 5 has a sum of 6, a 1 and a 6 has a sum of a 7, and then I'll go down here, I'll do a 2 then a 1, add 2 plus 1 and get 3, a 2 then a 2, add 2 plus 2 and get 4. So this is exactly the sample space we used in the last section. The reason I used it in the last section is just so you had an idea of what it looked like. So when I created it without a tree diagram, you kind of understood where it's coming from. It's not really rocket science what I'm doing. I'm just taking each one of these and pairing it with those. And then I'm adding the numbers under it. Because sometimes in the probability questions, we're worried about the sums, and other times we're worried about what's on each of the individual dice. The sample space is going to have 36 items because the first experiment is rolling 1 dice, there's 6 choices. The second experiment, there's the other dice, there's 6 choices. And that's how we get the 36 items that I'm making in my sample space. And then once you make these ones, you just keep it handy and you never make it again because it's a nuisance to do this, to say the least. Should have just brought that typed up version and said this is, but I just want, you can, just so you know that it can be done without, hours worth of work anyways. So now I'm matching the 5 with the 1, 2, 3, 4, 5, and 6. And again, to do this with a tree diagram, it's a really messy tree diagram. Not that this isn't messy when I write it. It wasn't so messy when I had it typed up. So these are all 36 things that can happen when you roll 2 dice and you have a first dice and a second dice. I don't know how readable it is, but hopefully based on what we did last time you can understand what this says. This is a sample space you're going to need to answer your questions in problem 25. So the number of points in the sample space for the first dice, any one of 6 numbers can come up, and for the second dice, any ones of 6 numbers can come up. So there's 36 elements in the sample space, all the way from 1, 1 to 6, 6, and with the sum added for extra bonus. So this, I didn't do a tree diagram, I constructed a table to list the sample space. Now we're going to do the probabilities. Each of the probability questions is going to have a denominator of 36 because there's 36 elements in the sample space. So when you do your probabilities for parts C, D, and E, your denominator is going to be 36, and the numerator is going to be the number of items in the sample space that have the look that you want. And we did these kind of probabilities in the last section, so hopefully you can do those with your own sample space. I'll do my probability questions. Answer each part of 25 except assume the first dice is a 5-sided dice and the second dice is a 4-sided dice. So my sample space is going to look different. So my first dice I put here. So my first dice is a 5-sided dice. So I'll put the numbers 1, 2, 3, 4, and 5 for my first dice. My second dice is a 4-sided dice. So I'm going to put the numbers 1, 2, 3, and 4. So for my dice, what can come up is a little bit smaller. I could get the first dice a 1, the second dice a 1, which is a sum of 2, the first dice a 1, the second dice a 2, which is a sum of 3, and I'll create the table exactly the same way, but it's just going to be smaller. Then first dice a 2, second dice a 1, first dice a 2, second dice a 2, first dice a 2, second dice a 3, 2 and a 4, 3 and a 1, 3 and a 2. And then once you do one of these, they're not hard. It doesn't matter what dimensions the dice are. So my sample space is not the classic dice sample space because my dice are different sizes. So my sample space has 20 in it because it has 1, 2, 3, 4 by 5. So my sample space of rolling a 5-sided dice than a 4-sided dice is going to have 20 in the sample space because the first dice, which is a 5-sided dice, can come up any one of 5 numbers. The second dice, which is a 4-sided dice, can come up any one of 4 numbers. So my sample space has 20 in it, and I'm going to construct a table to make any dice sample space. Now I'm going to do probability questions, and each of my probability denominators is going to be 20 because my sample space has 20 in it as opposed to 36. First one, I want the probability that I get a double, and 1, 1 is a double, 2, 2 is a double, 3, 3 is a double, 4, 4 is a double. There's 4 doubles in my sample space, so my numerator is going to be 4. So the first probability is going to be 4 in 20. I'm going to reduce that to 1 in 5. The second one is the probability that my sum is 7. Well, for my sum of 7, 5 and 2 make 7, 4 and 3 make 7, 3 and 4 make 7. Those are the only sums of 7. So my numerator for that fraction is 3 because there's 3 of them that are 7. Part E, find the probability that a sum of 2 is rolled. In my sample space, there's only one sum of 2. So the numerator for that probability is going to be 1. The probability that I get a sum of 2 is 1 in 20. And then part F, are you as likely to roll a sum of a 2 as a sum of a 7? No. I'm more likely to roll a 7. There's 3 ways to get a 7, but only 1 way to get a 2. So I'm less likely to roll a 2 than I am a 7 in terms of the sum. Okay, this I'll do with a tree diagram. Year 27, a coin is flipped, can get a heads or tails, and then a 6-sided dice is rolled. You can get anything number from 1 through 6. I think we did the sample space already, but you want to recreate the sample space, find out how many items are in the sample space, and then answer probability questions. That should be a D. I am, for problem 28, flipping a coin and then rolling a 5-sided dice. How many items are in my sample space? When I flip a coin, there's 2 things that can happen. I can get a heads or tail. And then when I roll my dice, there's 5 things that can happen because it's a 5-sided dice. My sample space is going to have 10 elements in it. I'll create the sample space right on this sheet. My coin flip could come up head or tail, and then my dice can only come up 1 through 5. So I could have a head, then a 1, a head, then a 2, a head, then a 3, a head, then a 4, and a head, then a 5. And then the same thing with the tail. I can get a tail and a 1, a tail and a 2, a tail and a 3, a tail and a 4, and a tail and a 5. So my sample space for this problem is head 1, head 2, head 3, head 4, head 5, and then tail 1, tail 2, tail 3, tail 4, and tail 5. So there's 10 items in my sample space. So when I answer my probability questions, my denominator is going to be 10. For part C, the probability that a head is both a head and an even number, a head is flipped and an even number is rolled. The ones in my sample space that fit that is, and that is. Those 2 have both a head and an even number. Any other one, it might have a head but it doesn't have an even number, or it has a tail. So my numerator for part C is going to be 2, and that's going to reduce to 1 in 5. My last part, I need a tail and a number less than 3. Numbers less than 3 are 1 and 2. So for part D, those are the things that I'm going to count. They have a tail and they have a number less than 3. I'm not going to count a tail and a 3 because a 3 isn't less than 3. So this also has a probability of 2 in 10, which now reduces to 1 in 5. Oh, 29, similar problem, flipping a coin and then using a number from 1, 2, and 3. There's going to be 2 times 3, 6 items in the sample space. You make your tree diagram and you answer the questions. You have to pause the video. I'm going to do 30, and that's going to be getting close to, and that is the end. So for 30, I'm going to flip a coin and pick a number between 1, 2, 3, and 4. So for the coin, there are 2 choices. It can come up heads and tail. And for the number, there's 4 choices. It can come up 1, 2, 3, and 4. There's going to be 8 items in my sample space. Now I'll create the sample space. I can get a head or a tail, and then after the head, I can get the numbers 1, 2, 3, and 4. So I could get a head followed by a 1, a head followed by a 2, a head followed by a 3, or a head followed by a 4. And similarly for the tail, I could get a tail followed by a 1, a tail followed by a 2, a tail followed by a 3, a tail followed by a 4. There's all 8 items in my sample space. My sample space is going to have head 1, head 2, head 3, head 4, tail 1, tail 2, tail 3, and tail 4. Probability questions are going to have 8s in their denominator because there's 8 items in the sample space. All right, find the probability that a head is flipped and an even number is selected. So head and even, that's a head and even, that's a head and even. There's 2 items in my sample space that are head and even out of the 8, so the probability is 2 and 8, which will reduce to 1 and 4. And then a tail and then a number less than 3, same 2 items, but now out of 8, and this reduces to 1 and 4. So hopefully I didn't rush it at the end, but I sensed that it was getting more boring than usual. So hopefully you got through all the problems. If you need to see 29 again, there's problem 29. You can take a stab at it. You pause the video because I'm going to shut the video down, and we're getting a big way through chapter 4. So we're almost through a third of chapter 4.